As you recall in our last video on integrated rate laws, we learned that we can find the order of a reaction by graphing concentration versus time. If it comes out to be a straight line like this, we know it's zero order. If it comes out to be a curve, then it's either going to be first or second. And so we have to re-graph it with different y-axes. This one would be ln. If it comes out with a straight line, then you know it's first order. And if you change it to 1 over concentration and you get this graph, then that's going to be second order. We also learned the half-life equations, which we see right here. And another little tidbit I want to give to you is that a zero order half-life is always going to cut in half. So that's a really good thing to write down. It's going to save you a lot of time on certain questions. So a zero order, the half-life will always cut in half. For a first order, the half-life will always be constant. It will not change. And also, all nuclear reactions are first order. So if the question tells you it's a nuclear reaction, right away you know it's first order. And lastly, the T1 half for a second order is always going to double. It's kind of nice to look at why that is mathematically. See how this has an A0 right here? A0 counts as like the initial concentration. Well, every half-life it cuts in half. So when this A0 cuts in half, since it's in the denominator, the half-life itself will double. In a first order, there is no A0 in the equation. So no matter how much amount you have, it's not going to change the half-life because there's not even an A0 in the half-life equation. And since the A0 is in the numerator here, then every time it cuts in half, the T1 half will also cut in half. So again, that's a really good tidbit to have for what we're going to do next. So let's take a look at this, and we're going to apply what we learned to the next page in the notes. So we have here some data. We have time and we have concentration of NO2. NO2 is one of the reactants in this equation. We are not actually going to concern ourselves with the carbon monoxide. So we are only concerned with the nitrogen dioxide in this. Again, we're going to graph first concentration versus time, and we're going to see if we get a straight line that looks like this. If we do, then it's zero order. If we don't, we're going to get a curve. And if it's a curve, then that means that it could either be first order or it could be second order. So if that's the case, when we get a curve, we're going to have to change the graph. If we are going to test out first order, then we're going to test it out with the ln of A, concentration, NO2, versus time. If we get a straight line, we know it's first order. If that doesn't work, we're going to try this graph with 1 over concentration versus time. And then if we get that to be a straight line, then we know that it was second order. So to do this, we're going to use our graphing calculator. I do have one here. And we're going to take a look at that right here. Okay, so make sure you switch your calculator on. And what you're going to do is you're going to go to Stat, and you're going to go to Calc. I'm sorry, Edit. Stat, Edit. So Stat, Edit, and then you're going to hit Enter. Now you have these lists. So I've already typed these in, and I made these list 1 and list 2. So I'm going to write here list 1. I'm going to write here list 2. So you're going to go ahead and type these into your calculator. Here they are. You just use these arrow keys to go down, and then you go to the right. You can go up, type all these in. Make sure that when you type these in, you only go up to the 18,000 because the other ones don't have data for that. So you only go to the 18,000. Okay, once these are all in your calculator, we're going to want to graph them. So what we need to do is we need to go to stat plot, which is second function y equals, and see how it says plot 1. I'm going to hit Enter. And when you do this, you're going to hit it to be on. And by the way, all these directions are in your packet at the end. So you can always have a hard copy of this. Plus, obviously, you can rewatch the video. Okay, so we're going to hit this to on, and we hit Enter. So now it's going to be on. You want to select this graph, the middle top graph, which will connect the dots for you. And you want to make sure you're plotting list 1 and list 2. And you can pick your favorite marker. Okay, now that we have that, we want to see the graph. So we're going to hit the button on the top right that says graph right here. Usually you don't see the graph, so you're going to hit zoom 9. Zoom is in the middle, so zoom and then 9. And that's going to give you this graph. This graph is definitely not a line. So we know for sure that this cannot be zero order. So we're going to take that off the list. So now what we need to do is we need to plot the ln. So we're going to make this, I'm going to change colors here so we can see this. I'm going to make this list 3. So I'm going to have to make another list. And what we want to do is we want to take the ln of concentration. So that is going to equal the ln of list 2, because list 2 was concentration, and we're going to take the ln of that. So to do that on a calculator, you're going to go back to stat and edit, and we're going to make a new list, list 3. So highlight list 3, but all the way up top, highlight it so that L3 is actually highlighted. You're going to hit enter, and now it lets you type in the bottom. So we're going to hit ln, and then to put list 2, you hit second function, the number 2. You'll see L2. You don't technically have to close the parentheses, but if you feel better about it, you can. And then you hit enter, and look at that. It fills in the entire list 3. So that saved you the trouble of having to take the ln of every single number of list 2. So now we want to graph this and see what it looks like. So we're going to go back to stat plot, which is second y equals. And now we want to tell it we want to do list 1 and 3. So hit enter. And now we go down and change it to list 3. Now we hit graph. Again, we can't see it, so we hit zoom 9. And looks maybe a little better, but not really linear. Okay, so we're going to try the final option, which is second order. So again, we're going to cross off first order. That did not work out. So we're going to try second order. To do second order, we have to now take 1 over concentration. We're going to make that a list 4. And of course, that's going to be equal to 1 divided by list 2. So we're going to go back to our calculator, tell it to do that for us. So we're going to hit stat, and we're going to hit edit again. And we're going to go to list 4. So highlight list 4 with your arrow key, get to list 4, hit enter. It allows you to type on the bottom. You're going to take 1 divided by, again, you want to write list 2. So second 2, enter. And it does it all for you. So those numbers are all 1 over the concentration. So now we're going to do is you're going to tell it on stat plot that we want to do list 1 and 4. So second stat plot, hit enter, go down to list 4 for Y list, second 4, hit graph, and then zoom 9. And there we go. That looks really pretty straight. 1 point looks a little off, but it's really good. So what we now realize is this reaction must be second order. So to write the rate law, we're simply going to write rate equals K times concentration of NO2 raised to the second. So that's called the rate law. If you want to write the integrated rate law, that's always nice to write in a y equals ax plus b. So what is the y-axis in this graph right here? It's 1 over concentration. So 1 over concentration of NO2 equals, now remember the slope, this is a positive slope, so it's going to equal just the regular constant because K is always positive. K is always positive. You got to get that straight in your head. So because this is a positive slope, the rate constant is the slope. If we had one of these with a negative slope, then the slope is the negative of K because K is always positive. So a negative slope would be the negative of K. Okay, my y-axis, my x-axis in this is time. So that's going to be there, plus the intercept. So the intercept is this point right here on the graph. And that point is 1 divided by the original concentration of NO2. That's what that little 0 means. It means at time 0, the concentration of the NO2. So now we want to find the value in the units of the constant itself, which is the slope. So the calculator will do that for us. So now what we do is you go to stat, we go to calc, And we go to 4, which is linear regression. You could just hit the number 4 or use your arrow keys. Now, here's the trick. And depending on your calculator, it may look a little different. This is a TI-83 Plus simulator, so it's a little older of a calculator. But I have to tell it what list I want it to calculate the slope for. So even though I just graphed list 1 and list 4, the calculator is automatically going to default to list 1 and list 2 for the calculating the slope, which of course it wasn't even a line, but it's going to give it to you anyway, the best slope you can get. So I have to tell it list 1, list 4. So I hit second function 1, comma, which is above the 7, and then second function 4 to tell it list 4. Hit enter, and you should get these values. Okay, so the slope is 2.10, 10 to the minus 4th. So I'm going to write that here. 2.10, this is k equals because it's the rate constant. And we'll write that. And then we need the units. So remember what we do? We always do the molarity inverse. So liters over moles. We raise it to 1 less than the power total. Since it was second order overall, I raise it to 1 less, which is first. So you don't have to write the 1, of course. And then you do put the unit of time on the bottom, which in this case was seconds. We do not ever raise that to a power. So it's always just the plain old unit of time in that experiment. Okay, so this is the value in units of k. So I'm going to write that down here just so we could see it, because we're going to need to look at that for something else in a little bit. So 2.10, 10 to the minus 4th is the A value. Now let's look at the B value. You can see it says 2.01. So we're going to write that over here. That's the intercept, 2.01. That's the intercept of the graph. Now let's pay attention to something else you noticed on my calculator that you may not have on yours. I'll tell you how to do it in a second. You see this R squared. So R squared, this is called the correlation factor. R is the correlation factor. A lot of times they square it just because it'll always come out positive, because sometimes this will be negative if it's a negative slope. So what does this mean? The closer this number is to the number 1, just 1, the more straight the line is considered. So our line is not perfectly straight, as you saw it had a little wiggle to it, but it was pretty straight. So our correlation factor was 0.999, and then if you square it, it's 0.999 again if you rounded it, which is very, very straight because it's very close to 1. And again, if it was a negative slope, then the R would be close to -1, but the R squared would, of course, be close to 1. Let me show you what it would look like if we tried list 1 and 2. So remember how list 1 and 2 came out to be a curve. So let's do stat calc, but let's calculate list 1 and list 2. Even though it was a curve, you could still put a line of best fit. It won't be that good, but you'll do it. So calc, linear regression, and then we're going to say list 1, list 2. So I could just hit enter because that's the default. But just to show you, oops, you're going to hit second function 1, comma, second function 2. And my numbers are going to come out to be, look at this, very much different. Look at this. And look, see how this is coming out to be a negative because that was a curve. Remember how it looked like, I'm going to circle it on the paper. Remember how it looked like, oh, yeah. It originally looked like this curve. So if you put a line of best fit, it would be, a negative slope. So if you look at this, look at this. This is 0.949, very much different than 0.999. Then if you square it, it turns it into a positive number, and even worse, 0.901. So not really close to 1 compared to what we could have had. Now, if you don't have this on your calculator, you can get that to display. How you do that is you go to diagnostics, which is the second function of the 0 button. So we're going to hit second 0, and it goes to catalog. Sorry, catalog is what it said above the 0, but we're going to go to diagnostics, which is the letter D. So you have to scroll down. It's alphabetical. I'm going to go to diagnostics on. Mine are on already, but yours might not be. So you're going to hit diagnostics on. You hit enter. And now if you do the stat calc, you will see the R squared and the R. It's definitely a good tool to compare how straight a line is. All right, now we want to do number 3, which is filling in the missing values. So if we want to fill in the missing values, we're going to need to use our integrated rate law, which is 1 over, so let's see what we have first. For the first one, we have the concentration of 0.422 for the NO2. I want to see what is the time. How long does that take? So if you do a little bit of common sense, and on an AP test, you might not even have to do the whole calculation if it's a multiple choice, because you could narrow it down. But you could see that 0.422 is going to fit right here in between those two concentrations. So the time must also fit between 1200 and 3000 seconds. So if this were a multiple choice, they would only give you one choice. You wouldn't have to do this calculation. But if it's a free response, you'd have to show your work. So let's do it. So the concentration is 0.422 molar. So I'm going to write that over here, 0.422 molar. And that's going to equal the slope, which we got is 2.10 10 to the minus fourth. That was a positive number. Now the time is what we don't know. And then we're going to add the intercept, which is 2.01. Now, you know what? I want to take a brief pause on this and point out something to you. The intercept, notice, in the integrated rate law is 1 over the original concentration. Well, what is that? The original concentration was 0.5. So 1 over 0.5, if you do that on a calculator, and hopefully in your head you can do it, is equal to 2. So that is the intercept. This 1 over initial concentration is 2. And look at what we got with the calculator, 2.01. So it's very close. So that's another little cool thing. You can see that the initial concentration is related to the intercept of your straight line graph. Okay, so if you're going to do this all out on your calculator, let's do the math for this and see what we get. So you're going to take 0.422. You could hit the inverse button right there. And then you're going to subtract 2.01. And then you're going to divide that by 2.10 10 to the negative fourth. And that's going to give you the time, which if we round it to two significant figures is 1700. So look, that makes a lot of sense because 1700 seconds fits right in this spot right here, just like the concentration of 0.422 fit in the zone right there. Now listen, you cannot do a little ratio. You can't say like 1200 is to X as 0.442 is to 0.422 because this is not linear. It didn't come out linear with this concentration. You have to put it into the integrated rate law. Okay, good. Let's get the last one. Switch colors here again. So let's say we're trying to get the concentration at 12,000 seconds. So now we're looking for the concentration of NO2. And then we still put in our slope 2.10 10 to the minus fourth. The time we know is 12,000 seconds. And then we add the intercept 2.01. So we take out our calculator, 2.10 e negative 4. Oops. 2.1 e negative 4. Then we're going to hit times 12,000. And we're going to add that to 2.01. But remember, that's going to equal the inverse of the concentration. So we have to inverse that. You can just hit inverse x to the minus 1. And you get 0.221. So 0.221 is this concentration, 0.221. Does that make sense? Let's see. 12,000 fits right in between here, between 9,000 and 18,000. And look, 0.221 fits right here between 0.250 and 0.174. So always do a little common sense check to make sure that that made sense. Okay, last but not least, we're going to go to the half-lives. So half-life is how long it takes for half of it to react. So remember, in the equations, we have half-life is equal to 1 over Ka0 for second order. So you have to pick the right green highlighted formula for the right order. So 1 over Ka0. So that's going to be the equation 1 over Ka0. That's going to be the half-life, first half-life. And that's going to equal 1 over the K, 2.10 times 10 to the minus fourth, times the original concentration, which remember we said was 0.5. So we put times 0.5 here. So we do the math for that. I'm gonna do it like this. I'm gonna take the inverse at the end. So 2.1 e negative 4 times 0.5, and then I'm gonna inverse that answer, and that's gonna give me the first half-life about 9,500 seconds, because this was all in seconds. This is 9,500 seconds. That's the first half-life. Let's see if that makes sense. Remember, what's going to happen is that half-life is how long it takes to cut in half. So we do have the exact data of cutting in half from 0.5 to 0.250. And look at the time here, 9,000. It's in the ballpark. Okay, this is with 2 sig figs. So the sig figs are not great in this problem, but it makes sense. Okay, that's the first half-life. How long does it take to cut in half the first time? Now we're going to get the second half-life. So that's going to be 1 over Ka0. But now be careful, because it's the second half-life. That means it's already cut in half one time. So the original concentration is no longer going to be 0.5. My new A0 is going to be 0.250, because that's the new amount after one half-life in order to get the second half-life. So this is going to be 1 over 0.210. 10 to the minus 4th. Now we put 0.250 here. And we're going to do the math for that. So let's grab out our calculator. I'm going to do it the same way I did before. 2.1 e negative 4 times 0.250. And then we inverse that, and we get 19,000. So this is 19,000 seconds. So what's interesting is that we'll see if it makes sense, first of all. So 19,000 seconds. We don't have 19,000 seconds on here. So I'm just going to go like this and write 19,000. And then does it make sense that we would have half of 0.250 right here, which is 0.125? Yes, it does. That's going to be a molarity, because this is less than the highest value we have right here. Like 18,000 was our highest time. Now we're at 19,000. So it's a little more than 18,000. And look, the 174, it went down even more to 0.125. Okay, another thing that we wanted to notice that I told you on the other paper is that the half-life doubles every time for a second order. And that makes sense, because look, it was 9,500 seconds for the first half-life, and then it takes an additional 19,000 seconds. Oh, so you know what? That's the second half-life. So I'm sorry, I shouldn't have even written 19,000. That's not right. 19,000 is on top of the 9,500. So you actually have to add the 9,500 to the 19,000, and you're going to get 28,500. That's going to be the total time. Okay, so that's the total time to fill it in if you had to fill in the chart, okay? But this was the answer for second half-life. That's how long it takes to cut in half the second time after it's already cut in half. But if you had to get the total time, like in this chart, you would have to add that on to the first half-life. All right, we're doing great. We have one more to do. Find the percent of NO2 remaining after 4,000 seconds. Whenever you have a problem that has to do with like how much is left after a certain amount of time, you're always going to be using the integrated rate law of y equals ax plus b. Okay, so again, the equation is 1 over concentration of NO2 equals the A, which is the 2.10 times 10 to the minus 4th times the time, which I do know is 4,000 seconds here. And then the intercept was, we know it was 2, but I'll just put 1 over the original concentration. Okay, so let's just get this all in here. We know that this whole thing is equal to 2.01 according to the calculator. So let's do that real quick. We're going to do 2.1 e negative 4 times 4,000 for the time. 4,000 equals plus 2.01. That was the intercept, which is the same as 1 over 0.5, essentially. Now, remember, that's equal to the opposite, the inverse. So you have to inverse that. So we're going to write that, and that's going to be 0.351. So this is 0.351 molar, but that's not the final answer. That's just how much is left after 4,000 seconds. This says what's the percentage left remaining. So you have to get a percent. It's always the part over the whole. So 0.351 is how much you have. Look at what you started with, which we've said a bunch of times, 0.5. You started with that. So that 0.351 over 0.5 times 100. Do that on your calculator. 0.351 divided by 0.5, and then times 100. So that's 70.2% remaining. So 70.2% remains. Now listen, I want you to really pay attention to this because there's trick questions. I don't want you to be that kid that forgets. So this is how much is remaining. This always tells you how much is left, okay? So just get that in your head, remaining. But of course, they could try to be tricky. And instead of asking you what percent remains, they could say what percent reacted. So if they say percent reacted, which is, of course, the opposite of what they're asking before, then you have to do 100 minus that, and it's going to be 29.8. So 29.8% reacted. Please, please, please read the question, because that one little word is going to throw off the whole thing. So every time you use the integrated rate law, it's how much is remaining. If they ever ask you for reacted, you got to do a little 100 minus that to get it to work right. Okay, so hopefully that makes sense. I'm going to stop this video right now, and hopefully we will get this all squared away.